Hello students, welcome back to the class Carboxylic acids. So in the last class we have seen classification of carboxylic acids. In this video we are going to study structure and bonding in carboxylic acids. So the general formula for carboxylic acid can be written as RC double bond OOH. So in this, oxygen is having two lone pair of electrons. Both the oxygens are having two lone pair of electrons. So in this carboxylic acid, CO single bond, in that the lone pair of carboxylic acid are given to this CO bond. So that it becomes C double bond O, so that the pi electrons of C double bond O are shifted to oxygen. They are shifted to oxygen. So we can write this as a resonance structure for carboxylic acid. So here oxygen loses a pair of electron, so that it gives that electrons to this CO bond, so it gets a positive charge. This oxygen gets an extra electron, so it gets a negative charge. So this is structure 1 and structure 2. So both are resonance structures of each other. Due to resonance, oxygen atom of OH group develops positive charge and has tendency to attract shared electrons of OH bond. So here the oxygen is having a positive charge, and among that oxygen and hydrogen, oxygen is more electronegative, so it has a tendency to attract this OH bond electrons towards itself, so that this H plus removal will be easy. So shared pair of OH electrons, so in the structure 2, oxygen having a positive charge, it attracts the OH electrons towards itself. Thus shared electron of OH bond get transferred towards oxygen atom and bond gets weakened. Thus release of proton becomes easy. Okay. These shared pair electrons are somewhat shifted towards the oxygen. Therefore release of this H plus becomes easy. So it forms carboxylate ion, and that carboxylate ion is resonance stabilized. So see here the structure 2, in that the OH bond electrons are given to oxygen, so that H plus is released. So H plus is released, and this is a carboxylate ion formed. And this carboxylate ion is resonance stabilized. See here, this is the structure 3, carboxylate ion is here. So the negative charge, that electrons are given back, so these electrons are given to oxygen. So here the negative charge electrons are given to CO bond, so that CO bond pi electrons are shifted to oxygen. So this oxygen gets a negative charge, and here double bond. So structure 3 and structure 4 are resonance structures of each other. So simultaneously both the oxygen, because the structure is same at both the side, so we can write the resonance hybrid of this carboxylate ion like this. Both the oxygen acquire slight negative charge and both are having partial double bond. So this is a resonance hybrid, and by forming this type of the resonance hybrid, the carboxylate ion is stable. So and compared to this carboxylic acid, here in the carboxylic acid, one oxygen having a positive charge, another oxygen having a negative charge. So it is less stable. But the carboxylate ion, which is having small charges on both the oxygens and partial double bond between oxygen, carbon and oxygen, so that it is more stable than carboxylic group. So So we can explain that the existence of resonance. So for this structure, here the resonance hybrid is existed and this is more stable. In between carbon, oxygen and carbon, there is a partial double bond is present and both are acquiring small charge. This is again confirmed. The resonance hybrid, formation of the resonance hybrid is again confirmed by the X-ray studies. The existence of resonance in carboxylate ion is supported by X-ray studies. This fact is supported by bond lengths. So that is, the bond length means in the carboxylic group, one carbon oxygen bond is double bond and another carbon oxygen bond is single bond. So carbon oxygen double bond length is 1.23 angstrom. Carbon oxygen single bond length is 1.36 angstrom. But when in a oxalate ion, for example, sodium formate is taken and bond length is measured. In the sodium formate, instead of one bond is 1.23 angstrom and another bond is 1.36 angstrom, both the bond lengths are 1.27. So actually, when there is a carbon oxygen double bond is present, we should get 1.23 angstrom. Another bond should be 1.36 angstrom. But here one is more than this carbon oxygen double bond. It is 1.27. Another one is less than this carbon oxygen single bond, that is less than 1.36. It is 1.27. So both the carbon oxygen bond lengths are 1.27. So it is in between 1.23 angstrom and 1.36 angstrom. That is in between carbon oxygen single bond and carbon oxygen double bond. So it confirms that in the oxalate ion, in the sodium formate, that is carboxylate ion, there is resonance hybrid is present, so that this ion is more stable due to that resonance. This measurement of the bond length also proves the presence of resonance in the carboxylate ion. So the stability of carboxylate ion can also be explained on the basis of molecular orbital structure. So this is one, that is by the X-ray studies also the presence of a partial double bond is confirmed. By the measurement of bond length also the resonance hybrid in carboxylate ion is confirmed. And then the stability of carboxylate ion can also be explained on the basis of molecular orbital structure. So in the molecular orbital structure, in between carbon, oxygen and carbon and oxygen, among these three, carbon and oxygen both are sp2 hybridized. So sp2 hybridized means carbon having 3 sp2 hybrid orbitals. So among that, the carbon forms sigma bond with adjacent oxygen, one sigma bond, another sigma bond with adjacent oxygen, and one sigma bond with R group, that is carbon or hydrogen, any other groups. So here 3 sigma bonds are formed, and this sp2 carbon having one unpaired pz orbital which is perpendicular to the plane. Like that, oxygen also. So in the oxygen, it is also sp2 hybridized and it also having 3 hybrid orbitals, Among that, one hybrid orbital forms a bond with carbon and it forms a sigma bond. Another two hybrid orbitals having lone pair of electrons. So these two are not involved in the bond formation. Now oxygen, both the oxygen having one pz orbital which is perpendicular to the plane. So in the both the oxygens, one unhybridized pz orbital is present which is perpendicular to the plane. Now the tendency of overlapping of unhybridized pz orbitals, sideway overlapping, both the side, the carbon oxygen overlapping on this side, carbon oxygen overlapping on this side is equal. So both the above and both the below orbitals are overlapping, so that it forms the structure like this. So above orbitals are overlapping, below orbitals are overlapping, and there is a cloud between these oxygens. This is the sigma bond. So this is 3 sigma bonds which are present here. The next, the cloud, electron cloud is present here above and below like this. So it can be represented by this dotted line. Oxygen, both the oxygens having a slight negative charge, and there is a partial double bond between both of the oxygens. So this is called molecular orbital structure of carboxylate ion. So this also confirms why there is no pure double bond or no pure single bond. So actually it is in between a single and double bond. Both oxygen carbon oxygen bond is partially, it is double bond. It is not a completely double bond or pure single bond. It lies in between that due to this overlapping of unhybridized orbitals. And this confirms the resonance in carboxylate ion, the resonance in the carboxylate ion. And due to this resonance, the carboxylate ion is more stable. It gives H plus easily. That's why it is acidic in nature. So let us see the acidic nature of carboxylic acids, the acidity of carboxylic acids. So when the compounds are called acidic, means if they are giving H plus ions, then they are called acidic. So carboxylic acids are acidic in nature. They are weak acids, hence they ionize in the solution partially. So like this, RCOH plus H2O, partial ionization that can be shown by reversible sign. It forms one carboxylate ion plus H3O plus. For the formation of carboxylate ion, it should give up this H plus. For this equation, for applying law of mass action, we get Ka. Ka is called dissociation constant of an acid. Ka. Ka is equal to concentration of ions. Concentration of ions, that is product of concentration of ions. There are two ions are there, and divided by concentration of the acid, RCOH. So here, as these ion concentration increases, Ka value increases. If the carboxylate ion formed is stable, then only the forward reaction takes place and concentration of ion increases, so Ka also increases. So Ka is called dissociation constant. Higher is the value of Ka, stronger is the acid. So Ka values of carboxylic acids are usually very small and consist of negative power to the 10. It is 10 raised to minus 5, 6 like this. So therefore, they are expressed in terms of pKa. So what is pKa? You already known, you have studied that is pKa is equal to negative log of Ka to the base 10. So when Ka value is more, pKa value is small. So greater the value of Ka, smaller the value of pKa. Some K and pKa values of some carboxylic acids are given here. Before that, we can see how it behaves as an acid. Means if it can give H plus easily, then it is called acid. So how it gives H plus easily, that we can explain here by this formation of the resonance structures. As we see in the carboxyl group, in the resonance structure of carboxyl group, one oxygen gets a positive charge, another oxygen gets a negative charge. So that it becomes unstable because there is opposite charges are present. But when it forms a carboxylate ion, carboxylate ion is formed easily because the oxygen is positive in charge, so that it attracts this OH bond electrons towards itself. So release of this H plus becomes easy, so that H plus is released and carboxylate ion is formed, and that carboxylate ion can be resonance stabilized. So by forming the resonance hybrid, the carboxylate ion is stabilized, and due to that it gives H plus easily, so it behaves as an acid. Let us see some pK and Ka values of some carboxylic acids that we already studied. We have seen the example. Formic acid, HCOOH. Ka value of formic acid is 1.77 into 10 raised to minus 5. Or if pK value is taken, then it is 3.75. Acetic acid, CH3COH, it is 1.75 into 10 raised to minus 5. So pKa value is 4.76. So see here, in formic acid and acetic acid, formic acid having more Ka value than acetic acid, or it having less pK value than acetic acid. This is because this K value shows that formic acid is more acidic than acetic acid. For that reason is, in the formic acid, what happens? CH bond is present. So CH bond is almost taken as a neutral. But in the acetic acid, one is CH3COOH. And when it forms a carboxylate ion, COO minus and H plus, and if it is more resonance stabilized, then only the Ka value increases. But here, the methyl group is electron releasing group. That is, it shows plus inductive effect that you learned in the last semester. So this methyl group releases electrons towards this carboxyl group, COO group. Due to this release of electron towards the group, this carbon becomes somewhat unstable. So it can't distribute this negative charge among itself properly, so that the K value is less than the formic acid. If you can explain the acidity of formic acid and acetic acid, means formic acid is more stronger than acetic acid. That is because in the acetic acid, methyl group shows positive inductive effect. It releases electrons towards the carboxyl group, and due to that the ion is less stable. That is, acetate ion is less stable than formate ion. Therefore, formic acid is more acidic than acetic acid. But in the chloroacetic acid, acetic acid, one hydrogen is replaced by one Cl. See the value, it is 136 into 10 raised to minus 5. Acetic acid is just 1.75, but chloroacetic acid is 136. That is again due to the inductive effect. In the acetic acid, only CH3COOH is present and methyl group is electron releasing group. But in the chloroacetic acid, CH2COOH, the chloride group is electron withdrawing group. It withdraws electron from the adjacent carbon. So that this carbon withdraws electron from this carboxylate group, so that carbon can easily distribute the negative charge which is formed on the oxygen. So that here the ion formed is more stable than the acetate ion. Therefore, it gives H plus easily. So forward reaction takes place, Ka value increases. So it is high, that is 136 into 10 raised to minus 5. So among these two, acetic acid exerts plus I effect. Chloroacetic acid exerts minus I effect. Plus I effect decreases the acidity of carboxylic acids. Minus I effect increases the acidity of carboxylic acids. So as the minus I groups increases, so dichloroacetic acid, so again the negative inductive effect is increased, so the Ka value is also increased. It is 5530 into 10 raised to minus 5, and vice versa, pKa values decreases. Benzoic acid, it is 6.46 into 10 raised to minus 5 and pKa value is 4.19. Para-nitrobenzoic acid, again here in benzoic acid and para-nitrobenzoic acid, the Ka value is increased because the NO2 group is electron withdrawing group. It withdraws electron from the benzene ring, so that benzene ring can take the negative charge from this ion, and here this is electron withdrawing group. So as the electron withdrawing groups are present, the acidity of carboxylic acids increases. See the example in benzoic acid and para-nitrobenzoic acid. Due to the presence of nitro group, the acidity is increased because the nitro group is electron withdrawing group. So it helps for the stability of carboxylate ion. In acetic acid and chloroacetic acid also, if the chloro group, that is electron withdrawing groups are present, they helps for the stability of the carboxylic acids. Therefore, the Ka value increases. But in acetic acid and formic acid, the acetic acid methyl group is electron releasing group. It decreases the stability of carboxylate ion. Therefore, its Ka value is less than the formic acid. So, as the plus I effect increases, the acidity decreases. But as the minus I effect increases, the acidity also increases. So while studying the strength of carboxylic acids, whether the electron releasing groups are present or electron withdrawing groups are present, on the basis of that we can explain the stability of carboxylic acids. So in the next class, we will see preparation of carboxylic acids. Thank you.